We talked about charge in the previous video and how electrons are responsible for the charging of an object. Addition of electrons making a object negatively charged, and the subtraction of electrons making an object positively charged, because you have a different ratio of protons to electrons. If protons to electrons ratio is 1, if there's the same number of protons as electrons, the object is neutral. It has 0 net charge. Add up all the positive charge from the protons, add up all the negative charge from the electrons, they balance out. If you're missing electrons, then those unbalanced protons give the object a positive charge. If you have an excess of electrons, those unbalanced electrons give the object a negative charge. Some objects, all objects contain atoms. All objects contain protons and electrons. However, some objects allow those electrons to flow more freely than in other objects. So we have two different types of objects that your book introduces. The first one are objects or materials that are conductors. Conducting materials allow charge to flow freely through them, not with 0 resistance, but with very, very, very small resistance. So if you need charge to move from one point to another, a conductor is the way to do it, which is why the wires in our walls, extension cords, high power lines are made of conducting materials. For example, copper is a wonderful conductor. Aluminum, salt water, iron, a lot of the metals are good conductors. On the other end of the spectrum, we have insulators. Insulators are materials through which charge does not flow freely. The material does not have a lot of free electrons that can move through the material. Materials like rubber or glass or air are good insulators. Now, just because an object is an insulator doesn't mean charge can't flow. It just takes a lot of force. We'll learn about a voltage later on. It takes a lot of force to push the charge through a insulator. So for instance, lightning. Lightning jumps through air, right? It's a large amount of charge moving through thin air. Air is a good insulator, so lightning requires a tremendous amount of force, electromotive force, to push it from one point to another. Now, these broad categories, objects don't necessarily have to fall into one or the other. We'll talk about that in a moment. Just because these objects are conductors doesn't mean they're all the same conduction ability. Some materials are slightly better conductors than others. Insulators the same way. Some materials are slightly better insulators than another insulator. Now, of these two broad categories, there are two small ones your book really doesn't mention very much. We'll introduce those here. There are superconductors. A superconductor is a material through which there is 0 resistance to the flow of charge, to electricity. This superconductor, it would be an amazing material if we could make them room temperature, because it would stop laptops from heating up. It would stop energy loss from transmission wires, which we'll learn about a little bit later. Superconductors are amazing materials, but none exist that work in a laboratory temperature, like a room temperature. Most of the superconductors we've created are low temperature superconductors. You need liquid helium or liquid nitrogen to cool these materials down to make them superconducting. At room temperature, superconducting materials aren't superconducting. And then finally, a semiconductor. Semiconductors are materials that are kind of midway between conductors and insulators, like silicon. Silicon is a semiconductor. It's not as conductive as a conductor, but it's not as resistive as an insulator. If you can dope silicon, if you add impurities to silicon, you can actually turn it into a decent conductor. And this is how circuit boards are made. A circuit board is nothing more than a silicon wafer with little tiny channels etched in with impurities that allow electricity to flow in the silicon. So semiconductor industry, Silicon Valley is often called, Silicon Valley is where computing really took place. Modern computers depend strongly on the existence of these semiconductors. Your book talks about how to charge an object by induction. Now, before this, charging an object, we talked about rubbing amber with animal fur or rubbing a glass rod with silk. You can charge an object by physically removing electrons from that object. Think about rubbing a balloon in your hair. If you rub a balloon in your hair, that balloon will stick to the wall. You can charge that balloon, the rubber in the balloon, by rubbing it in your hair. You're physically transferring electrons between the balloon and your hair. You're physically removing them through friction, through force. What if you don't want to touch the object to charge it? Well, there's a way of charging an object through a process called induction, or inducing a charge. So the steps for that will start here. We have an object that is a conductor, so charge can freely flow through it. And we have the positive charge here shown in red, the protons in the object. Again, the object has many, many more protons than I'm showing in this drawing. And each proton is balanced by an electron shown in blue. So this object is neutral. It has no net charge. It has the same number of positive as negative charges. Now I bring close to this object, so this is step 2 here, I bring close to this object a positively charged insulating rod. So this rod is missing electrons. It has a net positive charge. I bring it close, but I do not touch it to this conducting orb, conducting sphere. What ends up happening? Well, charge is free to flow. Specifically, electrons are free to flow in a conductor. So the electrons, they're attracted to the positive charge in the conductor, but now there's more positive charge over here. So some of the electrons, not all of them, but a small number of the electrons will get pulled to the left-hand side, attracted to this positive rod. Note this total number of positive and negative charges in this sphere is still the same. This sphere still has a net 0 charge. It's just we've redistributed the charge a little bit because of this positive rod nearby. Now I'm going to attach this conductor to the ground. And the ground is represented, this little black thing here is the wire. The ground are those 3 lines shown here. The ground means earth. When you have a grounding rod, you're basically, the earth is, think of it as an almost infinite supply of electrons. You can pull electrons from the earth or you can dump electrons into the earth. The earth doesn't care. The earth has a lot of electrons. So if I connect this sphere, this conductor, to the earth, to a ground, then the positive charge on the right, that's not balanced over here, starts pulling electrons from the earth because all of the other electrons over here are still attracted to that positive rod. But now I'm adding electrons to this conductor. So what happens when I break off the ground so electrons can't flee and I remove the positive rod? The electrons that came in because of the attractive electrostatic force from the positive charge near the ground wire, those electrons are trapped on this sphere. Because their conduction is a conducting sphere, the electrons are free to move. Electrons hate one another, right? Like charges repel. So the electrons redistribute themselves over the surface of the conductor. We'll talk about that later on in this chapter. But now you have more negative charge than positive charge. You have induced a charge, a negative charge on this object. What if we did the opposite? What if we brought in a negative charged rod? Well then, rather than collecting on the left-hand side, the electrons would be pushed away onto the right-hand side. When we established a ground, the electrons would escape through the ground. They would leave the conductor, be pushed away by the negative rod nearby. Not all of the electrons, but some of them. If we then remove that ground wire, those electrons can't come back. We've lost electrons, giving the sphere a net positive charge. So if I bring a positive charge to this conducting sphere, attach a grounding wire, I can give that sphere a net negative charge. I can induce a negative charge on that sphere. If I bring a negative rod close by, I can induce a positive charge on the sphere by letting the electrons escape and then removing that escape route. This is charging an object by induction.